over to you, Shomak. I'll give it to you as the moderator for this panel.
Thanks very much. Thank you, Anupama. Thanks. The other thing that is common between the three of us is we've known each other for a long time. I mean, I met Brian 35 years ago. I met Raja more than 40 years ago. So, you know, I've written papers with Raja. We haven't written papers with Brian, but we've known each other and our work for a long time. And so it's quite a rare thing to find amongst three randomly picked academics from across the world. However, this is not so random. And also, the other thing is that we all work in roughly the same area, which can be termed as observational cosmology, and which is actually a very, very interesting subject right now, with a lot of discoveries coming up, and a lot of discoveries that have happened in the last 2 or 3 decades, in which the people who are accompanying me on either side have played a very, very important role. So we know that we now believe that the universe started at a point, at a time which was about 14 billion years ago, and it's called the Big Bang. And since then, things have been expanding. So, and we also, over the last 100 years or so, know that only in the last 100 years, that we live in galaxies, which are kind of the basic building blocks of the universe. Now, let me start with Raja, because he's worked on galaxies for a long time, particularly the galaxies that are near our own galaxy, and to tell us a little bit about, you know, the role galaxies play in the universe, and what kind of interactions do galaxies have, what do galaxies do, why are galaxies so important?
So first of all, thank you, Shomak. Thank you, Ambika. Thanks, Brian. It's a privilege to be on this panel. This is my 3rd visit to Ashoka University. I'll say a little bit about why galaxies are important to me, and perhaps you will relate to this. Perhaps it'll make galaxies important to you as well. We are made up, we as human beings, and indeed the things, the notepad you're using, the pen, the chair you're sitting on, the desk you're sitting in front of, these are made up of elements in the periodic table. Elements other than hydrogen and helium. Hydrogen and helium are the first 2 elements of the periodic table, but it's really the rest of the elements of the periodic table that are important for complex molecules of the kind that our bodies are made of and the things around us are made of. And if it weren't for the fact that we live in a large dark matter-dominated galaxy, we call our own galaxy the Milky Way, but if we didn't live in a large dark matter-dominated galaxy, we wouldn't have the kind of periodic table of elements that we have here on Earth. I'm happy to back up this statement. This is not just my opinion. This is based on very strong evidence that it really requires a massive dark matter-dominated galaxies to have the kind of development of the kind of elements that make up our periodic table. This is why galaxies are important.
And and then these galaxies are embedded in what we call the expanding universe. Now, Brian, what's the universe? Why is it expanding? And why is that important for us to understand?
All right, so let's start with the universe, because this is where we're going to be controversial. We could probably all get into a fight about this. I'm going to define the universe as everything we have ever known and ever can know. Okay? That's going to be my definition. Other people will have different definitions. But anything that we can know about now or in the past, that's our universe. And it turns out when we look out from the Earth, and this is something that was done by Edwin Hubble in 1929, you look out and you see fuzzy blobs, galaxies, these things that Raja was just saying, we live in one. And when you look at them, the ones that clearly are a lot further away because they're small and you can't really see their stars very well, they are moving faster away from us then nearer by ones. But all of them, no matter which way you look in the sky, are all moving away from us. And so that was kind of a mystery when it was first realized in about 1917 that all the galaxies were moving away from us. And Hubble found out that the further away, the faster the motion away. And so if you think of just make in your mind's eye an expanding, for example, raisin bread that's in the oven. It's full of yeast, and as it expands, each raisin moves away from every other raisin, and no matter where you are in that raisin bread, as it rises in the oven, every raisin moves away from you, and it turns out, if you really think about it hard, the further away a raisin is from you, the faster it's going to move away as it expands. And that's why we give the idea of the universe expanding. You can also think of a balloon blowing up and putting points on the balloon, and the same basic idea occurs. So, yeah, since the 1920s, we've realized that the universe is expanding, and it turns out that Einstein's theory of general relativity, which is how we understand gravity, which he developed in 1915, actually more or less predicts this, although it took us about 10 years to realize it, and Einstein was sort of in denial about that until like 15 or 20 years. And so that's where we are with the expanding universe 100 years ago.
So then the question is, of course, what happens to the expanding universe? So say Einstein's theory predicts that the universe starts in a point and then it expands. However, if the universe is made up of matter, and we know that there's matter in the universe, you and I exist, we are made up of matter, and matter gravitates, the fact is that as the universe expands, there are these pockets of matter, which are galaxies, with lots of dark matter in them, and matter that you see. You expect that the universe, as it expands, is going to slowly slow down because the matter is going to pull the galaxy, the universe, towards being slowed down as it expands. Now, so for that, one needs to figure out how much matter there is in the universe. So the work on galaxies, Raja, how do you go and look at galaxies both nearby and far away to figure out how much matter there is?
So to measure how much mass is in a galaxy, not just the mass that's made up of stars or gas and dust, but the total mass in a galaxy, to measure that, it's really very simple. You use Newton's laws, and if you take the rotation speed of a galaxy, galaxies spin like frisbees. So if you take the rotation speed, call that v squared, multiplied by the radius of the galaxy, r, v squared r divided by the gravitational constant gives you the mass of the galaxy. So it's a very, very simple physics and math. The measurement is a little more difficult, but it's still not that difficult on the scale of things. So one of our colleagues, Vera Rubin, years ago, spent a career measuring how fast galaxies spin. And so once you measure v and can square that, you measure the size of the galaxy, so that gives you half of the diameter gives you a radius. V squared r divided by g gives you the total mass of a galaxy. And what Vera found was if you count the stars in the galaxy, you can also estimate how much mass the galaxy has in that way, and you get two very different numbers. If you just count the stars in the galaxy, you get a certain mass. If you measure rotation speeds of galaxies, you get a mass that's 10 times higher. 10 times, it's not a subtle effect, roughly 10 times higher. And Vera saw this galaxy after galaxy, including the Andromeda galaxy, and concluded that there is gravity in these galaxies associated with material that we can't see. So the term dark matter came to be, and this is, it's a very important element of the universe. And Brian's discovery, Brian, Saul, and Adam's discovery of the expansion accelerating over time, the discovery of dark energy, these two dark forces, dark matter and dark energy, dominate the energetics of the universe we live in.
Yeah. So getting ahead of our story, just talking about dark matter itself, I remember, Brian, Raja, we were all students, I suppose, at a time when this story was emerging of matter being dominated by unseen matter, dark matter. And people said, how can there be? Because the people didn't know what this dark matter was. Clearly, it was not things that make up the periodic table, which we call baryons. And so people often started thinking about how we could actually have something mimicking dark matter, but maybe we have the laws of physics wrong. You remember there are a lot of people who started changing the laws of physics. Do you want to comment on that? How you can change the laws of physics to kind of wish dark matter away and see whether we could still explain the universe.
Yeah, and so let me just talk a little bit as we go there, just how strong Newton's laws work. So if you do that v squared r over g, and you put in how fast the Earth rotates, which is about 30 kilometers per second, what our distance is to the sun, which is 150 million kilometers, and you calculate it, you get the mass of the sun, 1.989 times 10 to the 30 kilograms, right? And if you do that for Mars, you get the same answer. And if you do it out to Neptune, you actually get 1.990, and that's because Jupiter's in there, and it gives you that third decimal place. So it's insanely accurate. So when you start seeing things that are wrong by factors of 6, you know something's wrong. So one of the ways that people like to think is, well, maybe gravity's wrong. Maybe Einstein and Newton don't have it right. And let's imagine that the gravitational force becomes a little different if you get a long, long ways away. So these are called often modified Newtonian dynamics, Mond theories. And it turns out that if you want to go through and change the mass, you've got a new lever, and you can create a theory, and you can fit the data just fine. But that's because you've added something. You're basically given complete freedom to add something to physics, and it turns out that gives you the ability to kind of fit things. So you got to be really careful adding things to equations for no good reason, okay? So they did that, and then the question the rest of us have to ask is, well, does that break something else, okay?
So that's not how science works. You can fix something here,
Yeah.
but it also has to work there.
Yeah, it has to work everywhere. And it turns out, you know, the universe is not that easy to test these things, but over our careers, and, you know, we really have been people who have known and worked with each other since the 1980s, when I'm a little younger than these two. So I'm literally, they were the young hotshots when I was a graduate student. And so it's kind of taken 25, 30 years, in my opinion, to really say, actually, modifying Newton's law isn't going to fix everything. And we can talk about some of the ways that's true. That's more their work than mine. But it's illustrative of how science works, is you got to kind of try things out. People have ideas, and you don't get to just say, well, I don't like that idea. You actually got to go out and say, why do I think that idea is wrong, or why does it actually predict new things that I never thought of before? So that's the process we go through, but it actually takes a long time.
But then it gets resolved by the fact, I suppose, that there are other methods, not just the Vera-Rubin way of doing things. That you can.
So in fact, Mond fails for the smallest galaxies, for dwarf galaxies. And for those of you who like play on words, and those of you who follow French, remember Klipin, Anatoly Klipin, giving a talk that said "la fin du monde," as in the end of Mond, but it also translates to the end of the world.
Right, Mond meaning world, yes, of course.
So, but Mond again is modified, MO for modified, ND for Newtonian dynamics. So, and the modification was adding this A0 acceleration parameter and added added parameter to make things work. But as Brian said, it doesn't quite work everywhere.
But then you have other methods to find the dark matter, right? So not just dynamical ones, but I mean, care to talk about some others like gravitational lensing,
and X-rays,
X-rays and stuff like that. And so once and that's another way science works, is that if you find one way of measuring something, people will question it. And then you have to find other ways of measuring the same thing and coming to the right answer. So can you give examples from your work, for example, where when you looked at dark matter or looked at the matter content of galaxies?
In
found
ways
way,
other
yeah.
than measuring the spin rate of galaxies. A really a wonderful method that, again, goes back to Einstein's general relativity, goes back to 1912, 1915. Einstein, in order to explain Mercury's orbit, the perihelion precession of Mercury, and to explain Galileo's famous experiment, the Leaning Tower of Pisa, where things of different mass fall together, to explain these two things, came up with this revolutionary new way of thinking about gravity. Einstein says, don't think of gravity as a force, like Newton asks us to. Think of it instead as the distortion of space and time by the very presence of mass. Anytime you have something with mass, you distort space and time in its vicinity. The closer you are to that object, the greater the distortion, and the more massive the object, the greater the distortion. So one of the wonderful predictions of this new theory of gravity of Einstein's, it's called general relativity, one of the wonderful predictions was because space and time are warped, even light should be bent as it travels close to a massive object. And one of the predictions was light rays traveling close to the surface of the sun should bend ever so slightly. 1.4 arc seconds is the exact bending angle. And so the prediction was if you find a pair of stars whose separation on the sky is equal to the diameter of the apparent diameter of the sun, 30 arc minutes or half a degree, during a total solar eclipse, you should be able to see those two stars, but they look a little further apart than they are when the sun is in a different part of the sky. This was experimentally verified by Sir Arthur Stanley Eddington, later by W.W. Campbell. So this bending of light gives you another means of weighing objects. So you look at how distorted light is from, say, distant galaxies that are seen behind more nearby galaxies, and that's a phenomenon called gravitational lensing.
Yeah, and so you did quite a lot, for example, in your early work of looking at very distant galaxies and to find how the light bends around nearby galaxies or nearby clusters and measuring the masses of them. And then the answer is that at larger scales, even as you go from galaxies to clusters of galaxies, the amount of matter that you infer from these is much, much bigger than the matter you see in the stars themselves. And then that comes to, kind of mid-90s, when again we are, finishing our student careers and getting into faculty positions and things like that. And still people are scratching their heads on what this dark matter is. We've now established that it is there. It's gravitating, pulls, and the expectation is that as the universe expands, all this dark matter is going to pull it back. Hawking writes that famous book, A Brief History of Time, in which he thinks about if there's even more matter than is necessary, then it's going to pull the whole universe back after it expands to a maximum, and then it can come back all again. And there's all these wonderful possibilities, which of course, Brian, your work completely shattered. Because then in the mid-90s, the entire work of how the universe is expanding changed. Tell us that story.
Yeah, so we go back to 1994. I've just finished my PhD. We know about dark matter. It seems to be everywhere, but it's kind of hard to add up, right? Because you're looking at all these galaxies, and you can kind of see it galaxy to galaxy. There's a lot of extra dark matter, but what's going on, in between the galaxies? So one way, as Shomak just indicated, that we've known since the 1920s is that gravity will slow the universe down as it expands. So a great way to figure out how much dark matter is there really is not to mess around with the galaxies themselves, but to actually look at how the whole universe is impacted. And that means you've measured it all, there's no hiding it, it's all there. So we went on a program made possible by new electronic digital cameras that astronomy had helped really make possible. And then a way of measuring distances with these digital cameras way back into the past of the universe. So we could look really, really far away to objects whose light would take 5, even 8 billion years to reach us. And so those were supernovae, type 1a supernovae, and a group in Chile had really figured out how to measure their distances really accurately. They're just like giant, well, they're giant thermonuclear bombs, but you can think of them as giant light bulbs whose wattage we kind of understood, right? And so if you know how many watts a light bulb is putting out, then you see how bright it appears, and the further away it is, the fainter it's going to appear. So we could measure the distances quite accurately. So starting in 1994, we went through a project to systematically discover these objects, and we discovered over the period of 3.5 years, our case, about 15 of them, and we could measure quite accurately what the universe was doing back in time. And so the question is the universe slowing down a little bit so there's not that much dark matter, or is it slowing down a lot such that the universe would eventually go into the Big Bang of reverse, the Gnab-Gib, as we like to call it, the Big Bang in reverse. And so in the end of 1997, working with Adam Rees and a whole host of people around the world, we kind of looked at what the data said, and it was, the universe isn't slowing down at all. The universe is speeding up. And that was the wrong answer. That was not the answer we were expecting. It was an answer that seemed kind of crazy. And I will be honest, when I first saw it, I just said, Adam, what have you done wrong? And spent 6 weeks trying to figure out what he did wrong. And after 6 weeks, we realized he hadn't done anything wrong. And then we were worried about why this can't honestly be the correct answer. And you're worried about the things you hadn't thought about, no one had thought about.
So when you get an answer like that, I mean, I remember asking Vera Rubin this question. I mean, when she first found that these rotation curves are not coming down and there was dark matter, and I asked her, what she felt. She said, but there were people for decades who had talked about the presence of dark matter, like Zwicky and others. And in the general, community, people knew that there was a possibility that there is dark matter. But in your case, when you see a result like that, and that's actually completely unexpected. So what was the not just your reaction, but the community's reaction around you?
Well, it was not completely unexpected, but I would say any self-respecting cosmologist thought it was ridiculous. Okay? So it was an idea that even Einstein came up with in 1917 to stop the universe from expanding. And he later described himself acting like a donkey hanging on to the idea. He didn't say it was the biggest mistake of his life. He said, I actually was acting like a donkey. But it was ridiculous. Like, I cannot tell you, it was like a crank, there's some crank you meet out on the street who's telling you something that's ridiculous. I felt like I was having to go out and tell the world something that was ridiculous, that, I kind of like, I'm sorry to tell you this, but the universe, gravity is pushing, not pulling, and the universe is accelerating, and I know no one's going to believe me, but here it is. So it turns out when you go out with that, with fellow observational cosmologists, they correctly would say, okay, interesting, that's almost certainly not right. Let's go out and get more data and see what's going on. That's the right thing. But there were a group of theorists who knew that there was a problem in their model of the universe, of which it turns out this fixed a few things. It allowed the universe to not be curved. It sort of made their version of the universe that they wanted for maybe reasons we'll get to here, but basically it comes down to the theory of inflation. It kind of made it more credible. It also made the universe, it turns out, have the right age, because if you have their version of the universe was not going to be old enough relative to the stars that were clearly in it. And it also, very much, Shomak, in your area, fixed a problem, which is galaxies are kind of splattered across the sky with a pattern. And that pattern didn't really make sense, except for, it turns out, if the universe was accelerating. Then it made perfect sense. And one of our colleagues, George Estafew and a few other people, had for a brief moment said, well, the universe could be accelerating to explain this. And then, so he gets credit for that, but then in his next paper said, well, that's so ridiculous. It probably is how galaxies are formed, so let's just forget that and move on. So it did actually get some credence immediately because it fixed some problems. I'll be honest, I knew what our data said, but I knew there was a lot of things we didn't know, and I was genuinely 90% thought this is what the universe was doing, and I was 10% worried there was just something we were missing.
But that eventually led to the Nobel Prize, which we'll come back to later on. And it actually went to a Nobel Prize in a very short period of time because people realized how important this result was and how basically it changes our perception of the universe. Going back to Raja, I mean, you've dedicated a lot of your life to looking at our nearest galaxy, Andromeda. We started working together on Andromeda 40 years ago. Wonderful. But then the work that you've done with the largest telescopes in the world looks at how the Andromeda galaxy evolved and how it interacts with our galaxy. Mm-hmm. So tell us about hugely unexpected results there. And
I want to connect Andromeda to a couple of things that Brian and Shomak have been talking about. It's not quite true that every galaxy is moving away from us. Andromeda is actually moving towards us. And this is a really important thing about the expansion of the universe. You know, you can think of the universe as expansion of space itself expanding, but there are pockets of the universe where forces, like electromagnetic forces, in the case of this tabletop, or in the case of the solar system, gravity, forces like that can stop space from expanding. So, you know, this is important because if we lived in a universe where everything was expanding, including our rulers, then if you make a measurement between, let's say, our galaxy and another galaxy, and you use some ruler to measure it, that ruler could be the distance between the Earth and the Sun. If you use that ruler to measure distances to a galaxy, and let's say everything expands, let's say over time, everything expands by a factor of 2, guess what? Your ruler expands by a factor of 2. You'd measure the same number of ruler lengths to the same galaxy. In other words, if everything were expanding uniformly, you and I wouldn't be sitting here talking about the expansion of the universe. This is a very important thing. You know, it's like asking, if the universe is expanding, why are there traffic jams between Sonipat and Delhi? You know, there are pockets of the universe where the expansion has stopped. This is really important, and Andromeda Milky Way system is one of these examples where this has stopped. Can I say one other thing, please, about the age of the universe and expansion? Okay, so Brian mentioned Hubble's law, where you look, I'm going to give you an analogy. Let's say you look at a car. Suppose you had sort of very good vision, so you could see that there's a car that's 100 kilometers away from us, and it's traveling away from us at 100 kilometers per hour. Okay. Again, it's 100 kilometers away from us. It's traveling away at 100 kilometers per hour. There's another car that's 300 kilometers away from us that's traveling away from us at 300 kilometers per hour. There's another car 500 kilometers away, traveling at 500 kilometers per hour. If the cars are traveling at the same speed at all times, an hour ago, all three of those cars would have been at your location, right? Because 100 kilometers away, it's traveling at 100 kilometers per hour. So 1 hour ago, all the cars would have been at your location. In other words, if these cars were instead galaxies and you measured their speeds, you'd say that the beginning of the universe was an hour ago. This makes a very important assumption. It makes the assumption that these cars have been traveling at their current speeds at all times. If instead these cars are speeding up, then you make a mistake about how long ago they were at your location. In fact, you underestimate the age of the universe if you don't account for this acceleration. And this is the fix that Brian was referring to. I just wanted to bring that up with this analogy.
Absolutely. So that's wonderful. And then the other thing is, as you are talking about Andromeda falling towards us, the fact that the gravity between the two galaxies are pulling each other, there are other effects that come being also, and with things that you've found out, for example, that galaxies actually pull out stars from each other, right? These stellar streams that are joining. And so when you're talking about stars creating the elements within a galaxy, that might also necessarily not be true. In fact, I might be made up of things that have been made in stars in our galaxy, but also maybe other galaxies as well.
You're a product
right?
of cannibalization.
Yeah.
Exactly. We like anthropomorphizing galaxies. But, so in the work that you did with all these galaxies interacting with each other, any big surprises?
I think one thing that made my jaw drop has been the sheer size of galaxies. Andromeda, if you try to see it on a very clear night from a dark site, you might see the very central region of Andromeda, what we call the bulge of Andromeda. The disk, the frisbee-shaped disk of Andromeda, is, I'm going to use light years, it's about 100,000 light years in diameter. But if you look even further away, you see this very faint halo of stars, the kind that Beyonce has sung about, sorry, Beyonce wasn't thinking about the Andromeda galaxy, but Andromeda has a halo of stars. And that halo is not 100,000 light years in size, it's more like 2 million light years in diameter. So galaxies are huge. We are finding this out about the Milky Way. In fact, I have a PhD student defending his PhD thesis on Friday, and he's discovered that the Milky Way galaxy has a diameter of about 2 million light years. Now, if you consider that Andromeda is about 2.5 million light years away, this means that galaxies are practically touching if you consider their outskirts, not just
the dark matter halos.
And the dark matter halos around them. So it's no surprise that galaxy mergers or cannibalism events happen frequently because galaxies, especially if you consider their dark matter halos and their extended stellar halos, they're comparable in size to the typical separation between galaxies. This is not at all true for stars. Stars are much more compact than the typical distance between stars. So stellar collisions are very rare, but galactic collisions are very common.
So that means that Andromeda's stars and the Milky Way stars are already intermingling, right?
Absolutely.
And are certainly, I think, going to intermingle a lot more in the near future.
There's a recent paper by Alice Deason's student Til Sawala who's calculating the prediction. And this is, there's a close to 50% chance that there might be a flyby and not a head-on merger. So as we determine the masses of galaxies more precisely and their three-dimensional motion, we'll hopefully be able to pin down our future. Right now, our future is uncertain for a variety of reasons, politicians being among them, but the lack of knowledge of massive galaxies and how they're moving is a real reason for uncertainty in our far future, billions of years.
We'll come back to the science parts later in the questions. Let's, in the limited time we have, talk about your lives. What got you into astronomy?
Well, I mean, I'll
And
be
why
honest,
would
when I was your age,
these people get into astronomy?
I was going to be a meteorologist for most of you, and I went out, and that's someone who does the weather. I always loved the weather. I still love the weather. And I went and volunteered to work at the local forecasting office. This was kind of novel. They weren't used to people coming and said, I'll come and spend 3 months with you, but it seemed like a better thing than doing some horrible job. That would have been the alternative. And what I discovered was the forecasting office did forecasting, but they didn't do much science there. So while I was very appreciative of the experience, I realized suddenly it wasn't for me. And So in year 12, I suddenly had to decide, what am I going to go do at university? I had no idea. I knew I liked astronomy. The main thing I was worried about is I knew there were about 3,000 astronomers in the world who seemed to be the smartest people on the planet. I didn't really consider myself to be the smartest person on the planet. I was a very good student, but I wasn't the best person ever, and I'm just figured, okay, I can't be an astronomer, but if I do astronomy, I'm going to learn computer science, I'm going to learn physics, I'm going to learn math, I'm going to learn some engineering, and those struck me as being really useful skills in life. And I loved astronomy, so what a great way to learn these useful skills, and then we'll see what happens. Now, it turns out, my advice to you is think like I did when I was 17. You don't know what you're going to do. But if you want to do something, whether it be economics or law, whether or not you actually become that profession isn't as important as doing something you really enjoy that you're going to be really good at, because those skills are transferable. So I became an astronomer because I didn't know what else to do, but not because I thought I was going to be an astronomer. Yeah.
Would you say the same thing?
Yeah, I just want to riff off something Brian just said. You children have probably heard this from your parents many times, that hard work is the key to success. How many of you have never heard this before? No one, right? Okay, you've all heard that hard work is the key to success. I've heard this growing up. It's also true that it's difficult to work hard on something that you don't love. It's difficult to work hard just because it's going to pay a paycheck or because you have to. It's much easier to work hard when you love something. This is the reason to pursue something that you love or feel passionate about, because then it's easy to work hard. It doesn't feel like hard work anymore, and that is really the key to success. So for me, when I was your age, I knew exactly what I wanted to be. Unlike Brian, I didn't want to be a weatherman. I wanted to be an artist. I wanted to design logos. I wanted to work for an advertising agency, any advertising agency. I loved graphic arts. I still love art. And this is what I wanted to do. All the way through elementary school, middle school, high school, I was getting ready for my class 12 exam. That's what I wanted to do. The first college application I picked up was from the Government Art College in Kolkata next to the museum, Indian Museum. I never filled out that application because I was talked out of it by my grandmother, who told me that you can do art as a hobby while you follow science as a profession, but if you try to flip those two and become a professional artist, I doubt you could do science as a hobby. And she was right. Artists are much more open to amateurs joining them than scientists are to amateur scientists joining them.
Well, that's a great answer. So, but then the message, of course, for every one of you is very different as to what you want to do. But one of the things that I think comes out of this is that transferable skills are very, very important. It's important to know some skills to take on. Now, as you've gone on to become an academic, so you've made these discoveries, then you've run a university. But did you stop there? What else have you done that is really has been entertaining for you, has kept you sane outside academia?
Yeah, well, running a university was, definitely a big leap, as you are finding out right now. It's a very different thing than being a scientist. And I did that because I had passion about the importance of universities in society, and I wanted to help shape society as best I could by running and making sure, in my case, the Australian National University was going to be an outstanding institution, just like Shomac's trying to do here. The other thing that I started doing in 2000 as a young postdoc is I was living in Canberra, Australia, and I had developed with my wife a fascination for red wine. So we planted a vineyard. And many astronomers who these two people will know, literally out there with shovels helping plant them. And I make red wine. And that is, it's kind of more than a hobby, but it's not quite a full profession. So I make roughly several thousand bottles of wine, which are sold. And if you ever come and give a colloquium at Mount Stromlo Observatory, you get a bottle of my wine. It's actually very rare. It's very hard to get in short supply, but that's one thing I do. And the other thing that I'm doing now is I've become really interested in venture capital and how to take the ideas we have in astronomy and make companies out of it. And quite frankly, I'm thinking this is maybe a good way to fund astronomy given the current state of the world. So I'm on the board of a company that's taken technology from looking at how gravitational waves are created by emerging black holes, and we're creating a new way of doing measurement and test equipment. So oscilloscopes, if you know what those are, well, yes. Imagine making them purely based on a processor and software and configurable into all sorts of different instruments and being able to create kind of absolutely cutting edge bits that don't require lots of little parts the way you used to do it. So I'm doing that, and indeed I'm actually part of a venture capital firm that's set up in Canberra that funds a whole bunch of other ideas I don't even know yet. So I've kind of gotten into that because I've had a chance to see how the world works. I've got a lot of knowledge, and that's kind of exciting as well. And I'm continuing to do astronomy. I still love astronomy, but you can walk and chew gum at the same time.
Yeah, but also, yeah, that's right. And you see the connection between astronomy and the rest of society. And astronomy is given so much to the rest of society in so many ways. Raja, what keeps you sane outside doing astronomy? Of course, your art.
My art is an attempt to stay sane that's failing. I'm not sane. The thing that, there's a third thing that is that really I feel very passionate about. Some of you are in class 11. How many people? Quick show of hands, class 11. So when I was your age, when I was in class 11, my chemistry teacher got fed up with requests from students to get tutored, and he took one of these prospective students and handed them to me. So I started tutoring a class 6 student when I was in class 11. And for me, that was 47 years ago. That started a journey for me as an educator. I continued to tutor through the rest of my high school and through college. And ultimately, that's led a group of us to create programs for young people. There'll be 4 students from the Lodha Genius program who are going to be coming to my university this summer, in a couple of weeks actually, to take part in a program called the Science Internship Program. So it's a research program for students in the age range 14 to 17 to engage with PhD students and help them with their research. So that aspect, engaging youth in critical thinking in the context of research, is something that I'm really excited to wake up to every morning.
And putting them together with real research going on. Mm-hmm. Finally, I mean, before I hand on to the questions, all three of us are very passionate about cricket. And of course, today is the IPL final. And so, in general, so brief comments about cricket and cricketers and people you hang out with?
Well, I'm an American by birth, and so I've had to adopt cricket moving to Australia, and I adopted it in I got started when Australia beat the West Indies for the first time in like 2.5 decades, because I was on the telescope, and the games were on in the middle of the night, and we had a huge storm come in, and it was cloudy every night, so I watched the first test, and it was a really exciting test, and so I've kind of been hooked ever since. So my connection to cricketers actually comes from my trips to India. So I was, just before COVID, I was going down to Chennai, and I was sitting in the plane, and Glenn McGraw sat next to me on the plane and wanted to have a chat for 3.5 hours. And we had a great chat about what he was doing in cricket and my enjoyment of cricket. And then I was in Delhi 18 months ago with Adam Gilchrist as part of a Let's Talk About Australian Universities, and so got to know him reasonably well. And then the other cricketer that I've dealt with is Michael Hussey. Michael Hussey was trained as a science teacher. And so we did an event where we were explaining the physics of how a cricket bat works and willow and all sorts of stuff with him. as part of the National Science Center. So we're trying to scheme of whether or not we should do a cricket meets physics event here in India in the future. We'll have to see if we can pull it off.
There's a lot of physics in cricket. I remember as a student listening in on discussions between Ray Littleton and Jayant Narlikar, who passed away last week, on the physics of the cricket ball. I remember Littleton in those days had this long correspondence with Don Bradman, another big name, on how to handle, how to swing the ball, how to spin the ball. This is all big physics. Raja, any physics connection with cricket?
Yeah, absolutely. In fact, I invite you to come and take a look at my tie later. It's got a Don Bradman signature and an icon of Don Bradman batting. I knew this, it's not a coincidence, I knew this would come up today. So I wore this tie in preparation. So I've had the fortune of corresponding with Mohinder Amarnath recently. And I spent an evening with Sunil Gavaskar about a month ago. And I'm trying to connect with Kapil Dev. So the connection I see is, I've been an Indian cricket fan for a very long time, and the same cricketers that Brian talked about have been the bane of my existence because they've beaten the Indian cricket team soundly. They would, India, growing up as an Indian cricket fan, you guys don't know this, you're too young. Growing up as an Indian cricket fan in the 60s and 70s was heartbreak all the time. You knew you were going to lose. The only question was by how much. And the joke going around was the team couldn't catch the ball. They couldn't catch anything. The only thing they could catch was the common cold. So losing was a given. But it was also true that the Indian cricket team, it didn't surprise me growing up in Kolkata that everyone on the Indian cricket team spoke the Queen's English, whether it was Ajit Wadekar or Mansur Ali Khan Pataudi. They spoke perfect English, and we were growing up in India. It didn't strike me as odd that Indian cricket was drawing from a very narrow section of society. That has changed now, as you know. Interviews are conducted in Hindi very frequently, and players are drawn from all over the country, a wide range of socioeconomic strata. India's become a world beater in cricket now. I think this connection between being more inclusive, dipping into the full talent pool, and the excellence that the cricket team enjoys in India, this is not a coincidence. I think science hasn't achieved this yet. We are not as inclusive. We don't, group of scientists don't look like random drawings from the population. So while we're talking about all these wonderful successes in science, I think there's a lot more to be realized as we become more inclusive in science and indeed in other sectors of society. This is what I'm hoping to draw our cricketing friends, these cricketing superstars, into a conversation about making the world and society more diverse, more inclusive.
I think that's very interesting in academia as well. I think academia in India also is getting more and more diverse. Extremely diverse in many ways of how people are coming into higher education. And it's very interesting I think would be very interesting for people that you're talking about, the success and internationalization of cricket, the international success of cricket, to see how it's happening in India. In general, the internationalization of Indian education has also been fueled by a lot of diversity, a lot of people coming in from all over India with specific talents coming into higher education. It's helped us make India into a big academic superpower. So we can pause right now and see what what questions there are. I'll leave it to Ambika to figure out how to deal with the hands that are up.
Prof, we will get one right from the front, taking notes. So, yeah.
Hello. So I have two questions for Dr. Raja and one question for you, Brian sir. So the first question is, from our perspective, shouldn't we be technically at the center of the universe? From another body, how would that perspective look like? And if our galaxy wasn't dominated by dark matter, okay, sorry, that's a a point, my bad. The second question is, could you talk about how objects get redshifted as the universe accelerates? And my second question.
Just stick to one question.
Okay, fine.
Too many
Stick to
people.
one. There are many people.
I'm just going to say that we are not at the center of the universe. We are at the center of the part of the universe that we can observe. You know,
Yes.
the part of the universe we can observe today is equal to the speed of light multiplied by the age of the universe. Any sentient being or any being in the universe can claim to be at the center of their observable universe. There's nothing special about our location. I just want to say that we are, as Brian said, you know, in the raisin bread model, if you have an infinite loaf of raisin bread, you can put yourself on any raisin and every other raisin would be moving away from you. You're not necessarily at the center of anything.
All right, we just move there. Here.
Good afternoon.
Yes, yes.
Go for it.
I have a question for Dr. Brian. My question is that if we look at India's perspective, it's not very prevalent in the Western world, but if we talk about particularly India, then the field of astrology and the horoscope, they hold great value. 1.4 billion people, 900 million people rural, they believe in such things. So from the point of view of an astronomer, do these things make any sense or they're all hoax?
All right, so think of astrology as having a name in common with astronomy, but it's really a very different thing, okay? It's part of culture, and culture comes in all sorts of stories and myths and things, and these are important. I have my own set in Australia and the United States where I grew up. Every culture has it. Science is a philosophy where you take ideas and you make predictions. And these predictions are either right, in which case you keep making predictions, or they're wrong. Now, astrology can be used to make predictions, but you don't really have a way to go through and then, well, you could test them and say, are they making sense? And I think the scientific philosophy is about literally building and making things, understanding things through a very rigorous process. And so rather than worry about astrology, let's worry about science and using it for good use, and accept the fact that every human culture has these cultural things that have a sort of a mystic side to it. And it's okay to know and understand about it, but focus on the power of science and the good it can do. And if you keep that positive framing, I think that's useful as a way forward. That would be my advice.
Okay, we have a question here.
Yeah, good afternoon, professors. I just wanted to ask, do you think that dark energy is just a sign that our understanding of gravity is fundamentally flawed?
I have vested interest.
It's an excellent question. I would
But you should express it.
I think Brian mentioned this, that in Einstein's equations of general relativity, when Einstein first posed those equations, he didn't know that the universe was expanding. So it would be very odd to see an apple just suspended in air. If you saw that, if you thought the universe was static and there were apples suspended in the air everywhere, you'd have to invent something to counter the Earth's gravity to prevent those apples from falling. So Einstein came up and saw that in his equations there was a perfect slot for a term that would balance the gravity, the mutual gravity of galaxies. This is the thing he called himself a donkey for later, because Hubble soon discovered that these apples were not static, they were actually moving up, so it's as though someone had thrown them all up into the air. And then instead of slowing down, Brian and Adam and Saul have discovered that they're speeding up. And so all of a sudden, you're back to needing something that can push upwards against gravity. So there's a very natural slot for dark energy all the way back in Einstein's equations of general relativity. That doesn't mean that that's the only way to explain the accelerating expansion of the universe. But all I'm saying is, going back over 100 years, there's a mathematical framework for general relativity that naturally explains what Brian saw and Adam saw and their collaborators see in the expansion of the universe. So I don't think we need to, it points to a flawed gravity.
Yeah, and in the end, we have a theory that was invented way before the measurement was made and makes a very strong prediction. So the first thing we do is we go and we test that prediction again and again and again, and it's largely gotten the correct answer, but there are a few little cracks right now that we're not really sure about. And so that means we still need to get more data so that we are either sure we continue to get the same answer or we're sure something's broken in the model. So right now we're sort of, I'm kind of mixed. Are we seeing cracks in the basic model that Einstein came up with? I'm not sure. But I do know in the next 5 to 10 years, we will get enough data to, I think, be pretty confident we know the answer to that question. And so it's really a question of going out and measuring things, and if the model is broken, then we're going to need to fix it with a different way than what Einstein. And there are countless ideas out there. I have no idea which ones would be right. I don't even know if we need them at this point. So this is something for you guys to worry about, because it'll be your generation, I think, that figures this out, probably more than mine.
You know, these are very big questions. You know, there's job security in these questions because you're not going to solve these anytime soon.
You've got your hand up for a long time there. Yeah. Can I get a mic here first? Yeah.
Hello. So I had 2 questions for you. My first question is that you had mentioned, Dr. Brian, that light does bend in the universe. Does it bend only around black holes, or are there other instances when it bends?
Yeah, so I think Raja was talking about that any form of mass bends light. And indeed, the whole universe can be bent by the mass that's in it. When we're going through and adding up how much stuff there was in the universe, I said I wanted to see how much the universe was slowing down. Well, that mass can actually curve the universe itself. And so if the whole universe is curved by having a lot of mass, that turns out it actually magnifies distant objects when we look at them. If the universe is light, it's curved a different way, and it demagnifies objects. So what's in the universe actually curves space, and whenever space is curved, the objects are affected without exception. So it's everywhere in the universe.
And so light follows the curvature of the universe, right? So light will always follow the way the universe is curved.
I want to say one quick thing about the curvature of space-time. A convenient way to think about the curvature of space-time is, you think about light traveling in a straight line from point A to point B. When space-time is curved, light takes less time to follow a curved path from point A to point B than it would if it went in a straight line from point A to point B. That's the definition of curved space-time. Light actually takes a shorter time to travel in a curved path when you have curved space-time. And, when general relativity was first verified, it was the sun's gravity that was bending starlight ever so slightly.
Yeah, so it's like traveling to Australia on an airplane. You travel a curved path. You don't do the straight line because one's shorter than the other.
So thank you, Professor.
Just wait. More questions. We'll come back to it. We have time.
Good afternoon, professors. My name is Yashvardhan. So I just had a quick question. So how do current observations of dark energy informs us whether entropy can keep rising even if the universe were to recollapse or just end up in the big crunch?
Wow. All right, so this is a real technical question about how entropy, which is something probably most of the audience hasn't done too much with, but entropy is a way of kind of adding up randomness in the universe, okay? And there's some very fundamental ways of thinking about how entropy should always be increasing over time. And so I would say one of the things that people were always worried about was that imagine we had a universe that was created and then was and died, would it be recreated through a big bang, big crunch, big bang, big crunch? And it turns out it's kind of hard to make entropy work because you're always making more entropy, and the universe just wouldn't look the way it is. In the case of dark energy, there is I would say we don't yet have a consensus about how this is interacting with entropy. It's a very active area of study in certain camps. But my problem as an astronomer is I don't really have anything I can measure at this point as an observational. It's more of a thinking project at this point. And it's a way that we can assess some models around the creation of the universe and the Big Bang and see if they make sense. But I would say no clarity at this point from my perspective. Happy if you guys have any sense.
That's a great answer, Brian. It is, entropy is something that theorists worry about more than observers. Yeah. I have enough entropy in my living room and bedroom to worry about. I don't worry about it in the universe.
But then, the idea of the entropy and the big crunch probably comes from your reading Stephen Hawking's book, which was written in the 1980s. Brian's work with the accelerating universe now shows that the universe isn't coming back, right? So this whole question of the big crunch doesn't arise anymore. Anyway, next question out there.
Thank you so much.
Mike.
Good afternoon. I was wondering about the halo that formed around the Andromeda and Milky Way galaxies. A halo is like away from the center, right? Because it's like a ring around the galaxy. So how did it form like that?
That's a great question. So halos are not hollow at the center. So they're not shaped like, let's say, a shell. Halos are such that they're densest at the center, and so the number of particles per unit volume falls off with increasing radius. That's how halos are structured. They fall off in a particular way, as shown by computer simulations. Navarro, Frank, and White, a famous paper, NFW halos. So density falls off with increasing radius. So they're not hollow in the center, just to be clear.
No, I think, when you see religious figures, there are these circles around them. So they're also called halos.
That's right.
But these halos are not that.
They're not like Beyonce's halo at all. But there's an important thing about halos is the density falls off with radius, but doesn't fall off as steeply as the density of stars in a galaxy. So in galaxies, the stars tend to be more concentrated, meaning the density of stars also falls off with radius, but falls off more steeply than the density of dark matter. So as you go further and further out in a galaxy, you get more and more dark matter dominated. The central parts of many galaxies are not dark matter dominated at all. Does that make sense?
Raja, maybe you can talk just a little bit about how, stars are easy to understand, but you can talk about dark matter, about them being in orbits that are circular or ones that are like cometary orbits, and having to kind of sort that out to get what the shape's going to look like.
Yeah. We find that increasingly, as you go further and further out in galaxies, stars tend to be not so much in circular orbits as they tend to be more in plunging orbits. And when you're in a plunging orbit, you spend a lot of time far away. You go through the pericenter passage is very quick. The apocenter passage is very slow. This is following something like Kepler's second law. When you think about how fast planets move, they move fastest when they're in the part closest to the sun. Similar things happen in galaxy scales. So particles in halos are often on highly radial orbits, and they spend a lot of time far away from the center.
Okay, go that way. We need geographical diversity there, yes, of course.
So according to quantum physics, information can never truly be lost. But when we look at black holes and according to Hawking radiation, right, black holes evaporate over time. And considering how Hawking radiation is completely random, it does not contain information about the objects that actually fell into the black hole. So when the black hole completely evaporates, wouldn't all that information be lost? So isn't that a kind of a contradiction?
So I think this is, again, a place where we don't really have clear answers. If you look at information getting dumped into a black hole, so if you go jump into a black hole, not something I would recommend, because you will be spaghettified, that is, your feet are going to be pulled an infinite distance in front of your head, and that's not going to be good for your constitution. Now, through one of probably Stephen Hawking's most famous contribution to science, he realized that information doesn't come out, but energy can come out of a black hole through evaporation. And essentially, you get, through the Heisenberg uncertainty principle, a particle and another particle across the edge of the black hole, and the one goes out. And the information comes out without any information. It is what we call a black body of a specific temperature, depending on how big the black hole is. But unseemingly, that would seem to erase any information, okay? And I would say there are a whole bunch of schemes trying to reconcile that with other ideas that are completely unresolved. And there are thousands upon thousands of papers written on this, and my guess is none of them are right. But I could be wrong.
There's a very famous theorem called, very succinctly stated, it says a black hole has no hair. This is a theorem that John Archibald Wheeler, who's Richard Feynman's thesis advisor, came up with, and it's about loss of information. It's not about total loss of information, but it's about loss of all but 3 bits of information as matter falls into a black hole. You lose everything except mass, charge, and spin. I encourage you to read it. I love this theorem more and more as I get older, and I understand what it means to lose hair. But a black hole has no hair is actually John Wheeler's reference to himself, that all bald men look alike, and loss of identity is what it refers to.
Yeah. But let me just round this off with another aspect of this. One of the things that people often don't pay attention to is the fact that Hawking radiation is very, very slow. For a black hole that has mass the same as a star, to lose its energy due to Hawking radiation will take 10 to the power 60 years, 60. The universe is only 10 to the power 10 years old, right? So it's a very, very slow process. And there are other competing processes that would actually look at the information part of it that you're talking about, which are far more important than Hawking radiation. Anyway, who's next?
Hi sir, my name is Ria, and I've read that the universe is expanding faster than the speed of light, and Einstein has showed that nothing can travel faster than that. So what does this mean for humanity's scope for cosmic exploration and also cosmic observation?
All right, so this is a really interesting feature. So Einstein, just to be clear, what Einstein said is no mass can go faster than the speed of light, okay? What Einstein's theory of general relativity says is that space can be created, and space can be created faster than light can travel through it. So the universe is, right now, when you go to the really, really edge of the horizon, the reason the horizon exists is because beyond the horizon, space is being created faster than light can travel through it, okay? So it is a really interesting part that we're losing. We would seemingly be losing information, losing objects from the universe, although it's complicated. So when you take a picture from the James Webb Space Telescope and you look at one of the galaxies there, you're looking typically 10 billion years in the past. The light that that galaxy emits today, because presumably it still exists, will never get to us. It will be trying to get to us, and space will be created faster and faster and faster as it tries to get to us, and the photon will get stranded. It will never reach us. And so although we can see that galaxy now, and of course we're looking 10 billion years ago, the actual current information will never get to us. So it's a long way to say that, yeah, we live in a universe where we're losing effectively these objects over time, and that's because the universe is getting less and less dense as it accelerates. And if you go back 100 billion years in the future, we're just going to see a lot fewer galaxies than we see today. And the universe is going to be literally millions of times less dense than it is today. So it is all allowed by general relativity, but is, I would say, a little against your intuition that you're taught when you are given special relativity. Noting the creation of space is different than actual motion, and that's the important bit.
And I'll just add a quick thing to this to say, special relativity only operates in flat space-time. General relativity is a more general rule of the universe, and exactly as Brian said, the inflationary solution to the start of the universe, where things are expanding at the speed of light for a brief period, is completely allowed by general relativity. So in highly curved space-time, superluminal motion is allowed.
So building on from that last question, do we know by how much faster per se is the expansion of the universe in comparison to the speed of light? Is there like any constant for that, or do we have to find that out?
As you go, the way you need to think about it is, if I go far enough away, I will always exceed. In the universe we live in right now, if I go far enough away, because it's accelerating, I will cross the line where space is be creating faster than light can travel through it. And so I can't really put it any other way than that in saying the constant is the Hubble constant right now, and then what we measure in the acceleration is the next derivative. So the Hubble constant is the first derivative. If you know any calculus, most of you will not have done calculus yet. But the second derivative is how the change of the change is occurring. So that is the acceleration. So think of it as how a car moves faster and faster over time, as opposed to just how fast it's moving. So those are the two constants. And you can't put a single number on it. It depends on how far away in time and space you are to actually calculate it.
Take something from there. What? Okay. Can you give it to her?
Do you think that the universe could shrink as it's expanding, and like you said, space is getting created? Do you think it could be destroyed, like at some point in time?
So I didn't quite pick the question.
Yeah. So the question was, I think, about whether space can shrink. You talked about
like the way the universe is expanding right now. Like, do you think at some point it could start shrinking?
There are pockets of the universe that are shrinking, like the space between us and Andromeda. You can think of it as shrinking because Andromeda is moving towards the Milky Way. So in some sense, the distortion of space-time by mass includes pockets where the universe isn't expanding, where the expansion has either halted or reversed. So this is a very important difference between dark matter and dark energy. Dark energy, as far as we can tell, is uniformly distributed through space. There's some debate as to whether it's changed over time. Dark matter there's less dark matter in the universe than dark energy. It's something like 70% dark energy to something like 28% dark matter. So, there's more than twice as much dark energy than there's dark matter if you measure in energy units per energy density units. In spite of that, dark matter dominates in certain pockets of the universe because dark matter can be concentrated in space. It's not uniformly distributed. It's concentrated, and where it's concentrated is where we see galaxies. So galaxies are good examples of pockets of space-time that have stopped expanding, or pockets of space-time that are contracting. You can think of a collapse of a galaxy group or a galaxy cluster as space contracting. It's a perfectly valid way to think about how space-time is working.
Take something from the front here. Do you have a mic? Oh, there's a mic, yeah.
Good afternoon, professors. The question is, how feasible it is for us human civilization, to colonize Mars, as we said. How impactful would it be for us to witness our civilization reaching and settling other planets? How do you view this situation where companies like SpaceX are actively working towards making that a reality? Thank you.
Colonization of Mars. I'm going to hand this to Shomak.
So you're saying how likely it is? Or how long it will take?
How feasible it is for the human civilization to colonize Mars, and how impactful would it be for us to witness our civilization reaching other planets? How do you view this situation as where companies like SpaceX are actively working towards making this a reality?
I mean, I think it's inevitable. Whether I like it or not, that's a different question. But in the end, the colonization of the solar system will be driven by economics. Well, of course, that's how the Earth was colonized too. People went out and looked for unexplored continents to look at what resources they could extract from it, to look at mineral resources, to look at food resources, and things like that. And I think long-term colonization of the solar system is motivated by our long-term, interests of the corporate sector, as well as people who think that colonization of the moon, of Mars, and maybe mining of the asteroids, these are going to be very important once we run out of minerals on the Earth or natural resources on the Earth and things like that. So people are preparing for it. Personally, I think we are moving very fast, and that is also driven by economic things. You can see how the privatization of the space sector has accelerated in the US and in Europe. The total space economy now in this sector is about $500 billion. People think that within another 5 years it's going to go up to $1 trillion. Now, look at India. India is one of 5 big space powers, and we actually, within India, have less than 2% of this whole $500 billion industry. So that's why India also is opening up, and you can see the government control is opening up. A lot of people are going to do this. So we are now will compete over the next few decades as to how, just like we went and competed, putting our bases in Antarctica, thinking that we're going to be present there, we'll find ourselves competing for Moon, Mars, as well as other space missions. Now, how much economic yield these things actually give us will determine how fast this will expand, I think. I think we have no idea of predicting how mining the moon is going to be economical in the next 30 years or something like that. And people, like SpaceX, as you mentioned, are pushing it, not really knowing how much it's going to be very practical. Brian.
Yeah, I mean, I'll just say, absolutely agree with the way he's framed it. I'm much less optimistic of it making any economic sense in any amount of time. Gravity is a very weak force, but when you've got something the mass of the Earth, it's really painful. So trying to colonize Mars, I think we might have an outpost there, but I don't see it being an economic decision. I think it being waving the flag and saying we're here. It's just so much easier to, quite frankly, extract stuff from below the crust of the Earth if we really want to. We're going to run out of minerals, or maybe little asteroids that we can, get to come here. But one of my problem sets I do for our astronomy students is just do the energy economics of what it takes to get stuff here. And it's really, really hard. You want to get helium-3? That makes sense, maybe, from the moon? Hard to find too much else, I think, that makes a lot of sense. Even something like osmium is really, really hard to make an economic case for.
But there's another reason to get out there, longer term reason to get out there, which is when the sun bloats up into a red giant, we better not be here on Earth anymore, right? So, and Mars isn't far enough away, so we'd really have to go to one of the
Alpha
moons.
Centauri, well, or something else. Alpha
Yeah.
Centauri will be gone as well.
If humans are still there.
One last question. Where do you want to take it? Yeah? Wearing a NASA.
Hello. So professors, many physicists, they theorize that anything that goes into a black hole has to go somewhere, and that somewhere may be to another parallel universe. And I think Stephen Hawking also agreed with this theory. And moreover, the Einstein-Rosen bridge, which was also theorized, kind of proved and agreed with this. So what are your opinions on there being an existence of a parallel universe at the epicenter of, past the epicenter of a black hole, and how do you think we can do something with that knowledge?
So, general relativity is an amazing theory. It's also amazingly complex, and it allows you to create things that may not be real, even though mathematically they're possible. So the notion of having, for example, wormholes in space is clearly mathematically possible within general relativity. But whether or not they actually occur in nature, well, I think the evidence is there is absolutely no evidence that you can do it, despite it being a mathematical possibility. And it would appear that the amount of energy that is required to create one is a good fraction of the entire energy of everything in the universe. So I don't expect, Captain James T. Kirk, for example, to suddenly create a method of doing wormholes or warp drives. It's just the energy considerations are crazy. Now, never say never. Sometimes people are clever, so I'm not going to absolutely rule it out, but I would say extremely unlikely based on what I know.